So here is the new material for this section. Suppose you've got one function is always above another function on an interval from a to b, then we can give a single integral that represents the area between those two functions. So if we have sort of a scenario like this where here's our f of x, and here's our g of x, and here we have a, and here we have b. If I want to find this area right here, what do? Well, I simply take, and we saw that we kind of got our justification on this on the previous problem, we simply take the integral from a to b, and then we're going to take the upper function, f of x, minus the lower function, g of x. Okay? And by upper and lower, I don't mean in terms of relation to the x-axis, although it's true in this case. I mean which function has a larger, more positive y value than the other one. Okay? So I'm going to ask you to do 5, 6, and 7 and work through those. These are very explicit directions where I ask you to sketch several rectangles with a height f of x and a width dx. I'll do that one with you. So let's see here. Let's sketch a few rectangles with a height f of x. So there's one. So that the height of that rectangle is f of xi, whatever that is, and its width is delta x, or in fact we write differential x as it becomes thinner. And what I'd like you to do is, we're less concerned with actually sketching rectangles, and we're more concerned with which way those rectangles are slicing. So you can see that I'm just drawing slices of these really dx thin rectangles that have a height of just f of x. So that's what I want you to sketch. I just did it for number 1, and I'm asking you to do it in number 2 and number 3 as well. Okay. Number 3 is, of course, the most important one, where you're going to think about how these rectangles look. Okay. So if f of x is greater than g of x on the interval, we'll go ahead and call f of x the upper integral and g of x the lower integral. And so when we go ahead and integrate with respect to x, I want you to always draw these rectangles that are dx thick. So let's go ahead and do some of that here. Let me go ahead and draw a couple of these dx thick rectangles that look like this. So each one of these is a very thin rectangle that we'll call dx thick, and it's got a certain height. The question is what is the height of each one of these rectangles? Well, the height of this rectangle right here is this height, k of x, minus this height here, which is j of x. If I look at the difference between those two, I'll have the height of that rectangle. And that leads us to understanding how we're going to take the area between these two curves. We're simply going to take the heights of the rectangles, which is the upper curve minus the lower curve, and multiply that by the widths of those rectangles, which is dx. Again, we're doing this in a somewhat unrigorous way. We're just talking about this as a summing up. There's the sum from our integral symbol of a bunch of rectangles. This is the area of summing up the bunch of areas of rectangles. This is the area of a rectangle where this first piece is the height and this second piece, the dx, is the width. So that's how we're thinking about this problem. Okay, so I'm going to let you go ahead and answer questions 11 through 14.